Hello everyone, welcome to my channel Chem Insider. In today's video we'll be discussing about the remaining 4 topics of the valence bond theory, which we had discussed earlier. There are 5 particular types. Those are orbital overlap concept, directional is direction of orbital overlapping, and atomic orbital overlapping of these particular atoms. And then we discussed about the types of orbital overlapping and then the strength of sigma and pi bonds. So now we discussed about the first one, that is the orbital overlapping concept, where we learned that whenever 2 atomic orbitals come close to one another, they overlap with one another depending upon the attraction forces and the repulsion forces, right? Now we'll discuss about the second concept, that is of directional properties. Directional properties of orbitals. So the atomic orbitals of elements, the atomic orbitals of an element will be having certain directions. As we had discussed in the chapter 2, that is the structure of atom chapter, s orbital will always be in a spherical shape, right? S orbital will be in a spherical shape. It will be at the center of the coordinate axis x, y, z, whereas p orbital was a shape of dumbbell in the form of 3 particular axes: px axis in px, py and pz. So it clearly had 3 directions in it: px, py, pz. Similarly, d orbitals had 5 dimensions: dxy, dyz, dzx, dx square minus y square and dz square. So clearly an atomic orbital of an element has a particular direction in it. So in the valence bond theory, what we consider is this particular directional property of the orbital will be responsible for forming different geometry of a given molecule. In the case of our VSEPR theory, what we discussed was, we clearly explained the shape of the molecule but did not explain why was that particular shape being formed. Therefore, in the valence bond theory, we use these atomic orbitals and their particular overlapping concept in order to know the direction of these orbitals being in the particular overlapping formation, leading to the shape of a molecule. That is nothing but the directional property of the orbital. So for a valence bond theory to be successful, this is the main important point of this orbital property, that is a directional property, which explains the shape of the molecule being formed. Like for example, if we consider CH4 molecule, it is having a tetrahedral geometry. It is having a tetrahedral geometry. But we clearly don't know why it is having a tetrahedral geometry, right? So the reason for this tetrahedral geometry to be formed was clearly explained by the particular directional property of the orbitals. So when we come across the carbon present in the CH4 molecule, it has s and 3 p orbital. It has one s and it has one s orbital and 3 p orbitals, which clearly have certain directions involved in them, and those directions were responsible for forming a tetrahedral molecule in case of CH4. So the directional property of the orbital was very important in order to know the shape of the orbitals or shape of the molecule. Now the third point of the valence bond theory, which is that of overlapping of atomic orbitals. So okay, we have directions of particular orbital, and now how are they being overlapped and how are they giving a particular geometry? Overlapping of atomic orbitals. So how are these atomic orbitals being overlapped with one another? As we have learned, each of the orbital, it may be s orbital, p orbital, d orbital, they have certain number of nodes, right? So each of the orbitals have certain number of nodes. If you consider for the s orbital, it has 0 nodes, therefore it is spherical, and it will be having a uniform charge distribution along itself. If you consider s, it has a uniform charge distribution of plus in it. Whereas if you consider for p, it has 1 node, therefore whenever you consider any p orbital in any direction, it may be px, py, pz, it will be having a 1 node, that is where the probability of finding the electron is less. That is nothing but the wave function of the p orbital is less at a particular point, and on the other side it will be maximum, and the other side it will be negative. So like this, plus and minus. Similarly, when you come across d orbital, we have 2 positive and 2 negative. So now what are we going to consider is, we are going to just consider about the orbital overlapping of s and p orbitals. Now, if you consider the example of hydrogen molecule, if you consider the hydrogen molecule, it has 2 s orbitals, right? It has 2 s orbital, and we have learned in the first topic itself, more the amount of overlapping, more is the extent of overlapping, more will be its strength of the bond. Therefore, so whenever a bond has to be formed, orbitals have to be overlapping in a particular direction, which is discussed in the second point, as they have particular directional property. Therefore, depending upon this particular positive or negative sign, which we call them as phases, depending upon the positive or the negative phase, which is also called as the in phase or out of phase, and the direction of the atomic orbital, we can clearly relate the overlapping of atomic orbital. So therefore, while an atomic orbital is overlapping, it undergoes 3 cases of formation. One is in phase overlapping, second one is out of phase overlapping, third one is zero phase overlapping. So we have 3 types of overlapping. First one is in phase overlapping, second one out of phase overlapping, and we have the third one, zero phase overlapping. We have these 3: in phase overlapping, out of phase overlapping, and zero phase overlapping. So whenever 2 atomic orbitals of different particular phases come close to one another, they interact with one another in order to bind with one another in the overlapping form. And this overlapping occurs in 3 types. One is an in-phase overlapping, where their sign and direction both are same. Out of phase overlapping, where their directions are same but their signs are different. Zero phase overlapping, where their sign and direction both are different. So now let us consider certain examples of s and p orbital overlapping, which involves in phase, out of phase, and zero phase overlapping. If you consider for a molecule of having orbital CH4 molecule, if you consider the CH4 molecule itself, so what we have to do over here is, first we need to write down the electronic configuration of carbon. So electronic configuration of carbon is 1s2, 2s2, 2p2, right? 1s2, 2s2, 2p2. In the excited state, this is in the ground state, but in the excited state, carbon has 1 electron in the 2s orbital and 3 electrons in the 2p orbital, that is in px, py and pz. So for an atomic orbital to overlap with the other atomic orbital, it should be clearly half-filled in nature. If the atomic orbitals of one atom is half-filled, then only it can overlap with the other half-filled atomic orbital in order to get paired up those electrons. Now, if you write this, this is a 2s orbital, 2px, 2py, 2pz. Okay, 2px, 2py, 2pz. Now, if you write down the orbitals of overlapping, and since we have 4 hydrogens, each of these hydrogen will be having 1 electron in its 1s orbital. Now, half-filled 1s orbital of each hydrogen will be overlapping with the half-filled 1s, 2s, 2px, 2py and 2pz orbitals of a carbon atom. So, therefore, what happens is, in the first case, if you consider in-phase overlapping, first will be, if you consider this as a z-axis, so this will be the s orbital of hydrogen, and this, since it is in phase, what we have to observe over here is this positive and the positive of the p orbital. So p orbital usually have a positive sign and a negative sign. This is a p orbital. Okay, so positive of the p orbital and the positive of s orbital should be close to one another. Therefore, this results in a positive in phase overlapping like this, where the two electrons will be paired up. Okay, 1s orbital of hydrogen 1 electron, px orbital of this pz orbital of carbon will be of 1 electron, so it will be overlapping in such a way like this. Okay, or if you have to consider for a simple overlapping of ss orbital, so this is s orbital which has 1 electron, this is one more s orbital with one more electron. Now for the second one, that is 2s electron of carbon and 1s electron of hydrogen. So if these two come closer, what happens is they get paired up in such a way like this, overlapping happens and they will be paired up with a pair of electron. Okay, so this leads to two electrons present in the s orbital. What we are going to do over here is we can clearly write down the in-phase overlapping and out-of-phase overlapping for certain s orbital overlapping, pp orbital overlapping. So what happens when those two are interacting with one another and they are forming an overlapping structure? For the first one, in this left hand side I am going to take the in-phase overlapping and here out-of-phase overlapping. We'll discuss the zero phase later. First we'll write down the in-phase and out-of-phase overlapping. So now if I say for the in-phase overlapping of s orbital usually have just the in-phase overlapping. So this gives us orbitals like this. Okay, there is no out-of-phase overlapping for s orbital, but there is just only in-phase because it is always a positive charged species. Now if you have the second case, in-phase overlapping of p and s orbital, in-phase overlapping of p and s orbital, that will yield us geometry like this, that is hybridization like this with two electrons. And if you are considering for the out of phase of this particular overlapping, so what happens is the positive and the negative end will be in a reverted fashion and the positive of the s orbital will be in these two. So this will be leading us the out of phase overlapping. This will be leading us the out of phase overlapping. Okay, that is an out of phase overlapping where the negative of the p orbital is overlapping with the positive of the s orbital. Now for the in-phase overlapping of p and p orbital, positive, negative, positive, negative, gives us this type of orbital in the in-phase overlapping. In case of out-of-phase overlapping, positive, negative, positive, negative, they yield us an out-of-phase overlapping like this. So whenever you come across overlapping in case of in-phase, they combine with one another to form a bigger orbital, whereas if you consider for the out-of-phase overlapping, they get split up to form a smaller orbital. And in case of the zero phase overlapping, what we observe is the direction and the signs will be different. So now if you consider these two examples, so if this is in x-axis, this should also be in x-axis. If this is in y-axis, and then if you consider one more p orbital in the y-axis, that should always be in the y-axis. For in-phase or out-of-phase diagram, what we observe is both the directions of the atomic orbitals which are overlapping with one another should be in phase. Overlapping, in order to happen in case of in-phase and out-of-phase overlapping, the direction of both atomic orbitals should be in the same direction. That is, if it is in x-axis, the other one should be in the x-axis. If it is in y, the other one should be in y. If it is z, the other one should be in z orbital. Next, for the zero phase orbitals, what happens is, if we are considering the p orbital like this, which is, let us say, in x-axis, and this is the node center, right? And now if you are overlapping an s orbital on this with a positive charge, if you are overlapping an s orbital with this, it will be forming a zero phase overlapping. It will be forming a zero phase overlapping, such as like this. Okay, this is an example for zero phase overlapping. Or else, the one more example which you can take is, if we are considering this as a x-axis atom orbital, px orbital, and this is a pz orbital. This is a pz orbital. Then the overlapping of these two yields us zero phase overlapping. So what happens is, for a zero phase overlapping, directions will be different and signs will also be different. If you observe over here, there is zero probability of finding the electron at this nodal center, but there is a maximum probability of finding the electron at this nodal center. Therefore, once you combine these two, the probability of finding an electron will be completely depending upon the s orbital but not on the p orbital. So in such a cases we call them as zero phase overlapping. And further, what we have to observe over here is, if you consider for the CH4 molecule, that is a carbon tetrahedral CH4 methane molecule, which forms a tetrahedral geometry, we discussed that tetrahedral geometry should be having 109 degree 28 minutes of bond angle, right? 109 degree 28 minutes of bond angle. Now, as I said earlier, carbon in the CH4 has 1 electron in s orbital and 3 electrons in the p orbital. And further, the 3p orbitals, that's 2px, 2py and 2pz, are perpendicular to each other in the coordinate axis. If you consider these three are the axis of carbon, if this is z, x and y, the 2px, 2py and 2pz orbital, all the three will be in a different direction. That is, each of them will be in 90 degree to one another, right? So therefore, if this is a 2pz and 1s orbital overlapping over there, 2px being overlapped with one other orbital, 2pz is overlapping with 1s of another hydrogen. So clearly the bond angle between these three orbitals will be 90 degree, right? So if you consider carbon-hydrogen orbital, carbon-hydrogen bond angle, in case of these three conditions, which should be in, this one is in z-axis, this CH bond is in z-axis, this CH bond is in x-axis, this CH bond should be in y-axis. So if each of the bonds are present in three different coordinate axes, each of them should be having a bond angle of 90 degree. But what we have observed is, here there we have 109 degree 28 minutes of bond angle, and clearly the s and s orbital, the 2s and 1s orbital overlapping of carbon and hydrogen does not explain the interpretation clearly. If you consider the 2s and 1s orbital, and if you consider these three bonds of 90 degree, then the geometry of tetrahedral will not be formed because these three bonds angle of around 90 degree. So this is the point which have to be remembered for the longer cases. Now, for the types of overlapping or types of bonds resulting in the overlapping. Next is the fourth point. Next is the fourth bond, types of bonds formed. Types of bonds resulting in the different types of overlapping. So there are two types of bonds which can be formed. One is a sigma bond and the other one is a pi bond. One is a sigma bond, the other one is pi bond. So sigma bond 2 takes place. For an atom orbital to form a sigma bond, what's the necessary condition is, both of them should be parallel to one another. Both the orbitals should be parallel to one another, and further they have to be parallel to the axial axis. That is, if you consider this as pz orbital, and this is the pz orbital of one more atom, let me write it in a different color. Okay, so whenever you have to consider for the atomic orbitals which are to be forming a sigma bond, they have to be parallel to their axial axis. Okay, so if you consider these axial positions, they have to be parallel to one another and they should be forming an in-phase overlapping, and further in this particular in-phase overlapping they will be overlapping in head-on collision, head-on overlapping. If you consider this as plus and plus, these will be overlapping on the head over the head. Okay, so these will be overlapping on head-on overlapping. That is, the head of one orbital will be overlapping with the head of the other orbital. Okay, so whenever you come across the overlapping where the two orbitals are going on a head-on overlapping type of a bond formation, then those bonds formed are called the sigma bond. So there are three types of overlapping, that is sp overlapping, that is sp sigma bond, pp sigma bond, and ss sigma bond. First one is SS sigma bond, SS sigma bond. Second one SP sigma bond. Third one is PP sigma bond, SS sigma bond, SP sigma bond, and PP sigma bond. So what happens here is, in the SS sigma bond, S orbital of one atom will be overlapping with the S orbital of one another atom. S orbital of one atom will be overlapping with the S orbital of another atom, and this will be a head-on overlapping. And this is parallel to the axis of the molecule. Okay, this will be parallel to the axis of the molecule. That is nothing but the axial overlapping. Head-on overlapping is also called as the axial overlapping. That means the axis of the orbitals should be parallel to the axis of the molecule. If you consider hydrogen molecule, if this is the axis of the hydrogen molecule, the orbitals of hydrogen should be in parallel to the axis of the molecule. Okay, if you come across axis of a molecule being parallel to the axis of the orbitals, then those type of bonds are called the sigma bonds. See here, this is an SS sigma bond. Now for the SP sigma bond, if you consider this as z-axis of a p orbital, and then it should combine with the s orbital which is in the z-axis, which results in overlapping in this type. This is again head-on overlapping, and which is also called as the axial overlapping. Next, for the PP overlapping, if you consider this as a p orbital of one atom in the x-axis and the p orbital of one other atom in the x-axis. So if this is x and this is x, so these two get combined to form PP overlapping. Okay, so there are three types of sigma bond possible. One is SS sigma bond, SP sigma bond, PP sigma bond. So these are the three types of sigma bonds which are formed. Now for the pi bond to be forming, it should always involve p orbital. Pi bonds will always be formed by the overlapping of p orbital, but in this case the axis of p orbital should be perpendicular to the axis of the molecule. The axis of the p orbital should always be perpendicular to the axis of the molecule. If the axis of the p orbital is perpendicular to the axis of the molecule, if this is in x-axis and this is in z-axis, if the axis of the p orbital is perpendicular to the axis of the molecule, then what happens is the positive and the positive end, negative and the negative end will be overlapping sideways, such as like this. So this type of bonding, where the orbital of the axis of the p orbital is perpendicular to the axis of the molecule, having an overlapping on the sideways overlapping. Sigma bond is head-on overlapping, whereas the pi bond is nothing but the sideways overlapping. Then that type of particular bond formed because of this sideways overlapping is called pi bond. Pi bonds are those compounds where the electrons, where the orbitals of the atom will be overlapping in sideways. An important point which have to be reminded over here is, Sigma bonds are always formed if there are half-filled electrons present in the orbital. Sigma bonds are formed when there are half-filled electrons present in the orbital. Pi bonds are formed when one of the half-filled orbitals is fulfilled by one more half-filled orbital. That means pi bonds are always formed after at least one sigma bond has to be formed. If a molecule does not have a sigma bond, then it will not form a pi bond. Okay, so what we have to remember over here is, for a pi bond to be forming in a molecule, it should always contain at least one covalent sigma bond. If the molecule does not have a sigma bond, then it won't be forming a pi bond. Okay, so this is about the types of bond because of the overlapping. There are two types of bond, sigma bond and pi bond. Next is the fifth point, that is strength of these two bonds. Strength of sigma and pi bond. So whenever you consider for the strength of sigma and pi bond, we can clearly say that pi bonds are a lot weaker when compared to sigma bonds. That is because these two bonds, which can also be interpreted as like this, if this is the axis of the molecule, these two bonds, electron cloud, will be present above and below the axis of the molecule. That is nothing but the plane of the molecule. The electron clouds in case of pi orbital, pi bonds, will be present above and below the molecule, above and below the plane of the molecule. But in case of the electrons in the sigma bonds, will be on the plane of the molecule. Right? So electron cloud of the molecules forming a sigma bond will be on the plane of the molecule, whereas in case of the pi bond, the electron clouds will be present above and below the plane. Therefore, the extent of strength for sigma bond and pi bond is greater in case of sigma bond and less in case of pi bond. So greater the electron cloud present, greater will be the strength of the bonds. Okay. So this is all about the overlapping and bond formation of a given molecule in the atomic orbital explained by the valence bond theory. In the next class, we will be discussing about hybridization and types of hybridization for a molecule to form a definite geometry. Okay. Thank you for watching.